Okay, and next presentation is the last presentation. No, so fourth presentation. Okay, not last. The title is a passive gripping foot for electric robot to move over rough territory. The presenter is a Sho Hakamada. Mr. Sho Hakamada, please.
Okay. Can you hear me?
No, not yet. So I'm waiting for. Maybe as you started to share. It's a little.
Okay.
So I'm waiting. So please one more.
Okay. Okay.
Okay. I can see your slide. Okay.
Voice is okay.
Yes, I can hear you. Okay.
Okay. Thank you, Mr. Chairperson. I'm Sho Hakamada from Future University Hakodate in Japan. Today, I will talk about the passive gripping foot for a leg robot walking on a slope in rough terrain. And there has been dramatic increase in leg robots. For example, leg robots are applied to rescue operations and exploratory in rough terrains with uneven surfaces. It is dangerous for people to walk in rough terrains because there are a lot of obstacles such as sand, various sizes of rocks, debris, and fallen trees. In rough terrains, there are a lot of advantages of leg robots. They establish contact with the ground in selected points in accordance with the terrain conditions. Moreover, they can stride over large obstacles. However, when they climb on the slope in rough terrain, it is difficult to climb because they slip on the slope. If they have installations fit glass objects, they can climb easily. I will show you a similar research. This research shows a rock climbing robot that can move on the slope and walk at an angle of over 90 degrees. The robot has a gripper which has over 250 microspines. By hitching many microspines to the slope and wall, the robot can climb. However, it is considered that there are some problems for the rock climbing robot. First, it is too strong to grasp objects because microspines are broken. Second, the robot's installation is heavy, so the mobility of the robot is declining. So we propose a new gripping hood. The gripping hood can grasp ground passively without using energy and heavy installations. We use a mechanism of particle jamming as reference. First, this research uses universal robotic gripper. This gripper has a single non-porous elastic bag filled with granular matter. By using the elastic bag, the gripper can grasp various sizes of objects. Second, this research is also used the mechanism of particle jamming. It consists of an airtight enclosing membrane and a filling material for granular jamming. The gripper can generate a large surface area in contact and leads to less penetration in sand for a given mass of robot. However, the jamming foot needs a power source and its controller to inflate on the ground. Also, the airbags are easily torn up. So it is difficult to use on jagged terrain and difficult to attach on an existing robot. And we propose a new jamming gripping hood that is easy to attach on robots and that is strong under jagged terrain. The foot is made of linkage and causes jamming effect by applying weight on top. It is like a shoes for leg robot. The linkage forms a jamming effect after touch jam, so it is attachable to many of existing robots, like a human wearing shoes for working environments. From here, I will show you the design of the foot. This is the 3D models of our gripping hood. These models are consisted of one base, three nails, three fixtures, and three threads. And these images are 3D printing models. To assemble the gripping hood, the joints of the parts are screwed. The gripping hood has two colors of the resin materials, but the performance is the same. Our idea is using repulsive force of magnet. Two magnets are set to the base and the nail. As the threader is pushed by the ground, it drives the nail to perform a biting action. Repulsive force between the base and the nail, which is needed to move back the nail to its original position, is provided by a small magnet placed at the bottom of the base and the nail. Explain the diagram of mechanism movement and the static force produced by the nails in detail. Left diagram describes the force generated by the nail when the robot moves its leg to a stance phase. First, the robot moves its leg to a stance phase. During this, the threader touches the bump on the ground. Second, reaction force from the ground pushes the threader upwards. Third, the nail part is applied turning torque at the joint 1 by the threader. Fourth, the nail turns at the joint 2. Finally, the torque around the joint 2 generates a force at the top of the nail to push the bump from side direction. Right diagram describes the detaching action of the nail after the robot lifts its leg to change to a swing phase. First, the robot lifts its leg, which removes reaction force for the threader from the ground. Second, the threader is pushed back its original place by the repulsive force generated by the magnet. Finally, this turns the nail back at joint 2, which loosens the grasp motion of the nail. After assembling the gripping hood, we examine the performance and the grasping force. When 300 grams weight is set on the gripping hood, the force was measured as 0.53 newtons at each nail. Since the nail is designed to latch the foot to the vertical direction so that it does not lose contact with the ground, the amount 0.53 newtons should be sufficient to move the nail to the latching position. Next, I will talk about the experiments. This is a prototype robot which uses in the experiment. We attach the gripping hood to the KX-6 leg robot as in this picture. To test in real environments, we prepared an artificial stony rough terrain. Surfaces are horizontal or 20 degrees inclined. On the surface are 1 centimeter rocks, and the rocks are connected into 8 centimeters bumps as in this picture. We prepared a flat foot as in this picture and compared the walking distance after five steps. Also, we observed the grasping motion during hill climbing and checked if the foot could grasp the bumps. An experiment movie is here. First, I show you the experiment movie in horizontal field. Both robots were able to move mostly the same distance after 5 steps. But the grasping foot moved a little bit further than the flat foot. This was because the gripping foot did not slip on the bumpy surface. Next, I show you the experimental movie in a slope at 20 degrees. As you can see here, the gripping foot could grasp on the bumps, and the distance was 8 centimeters compared to 4 centimeters. The grasping motion often failed to pinch the bumps, but the climbing was achieved by nails that catch the bumps. Next, from the experiment, the gripping hood could give better climbing performance. However, the success of grasping depends on the size and height of bumps. Especially, shallow bumps was hard to grasp since it does not have enough stroke to push the nails. But it was also shown that the nail still keeps hanging on the bumps. In conclusion, we propose a new gripping hood that is attachable to existing rake robots. The hood is made of linkage and it grasps objects on terrain by passive jamming effect after touchdown. Grasping and releasing was done by step and lift movement only. So it is easily attachable to rake robot, like wearing shoes. This presentation was a first step to realize passive hard jamming grasping foot. At this moment, the performance is limited by the size of bumps. So we plan to investigate more flexible and compact design, which can grasp wider range of obstacles. That brings me to the end of my presentation. Thank you for your attention.
Thank you for interesting presentation. So is there a question from audience?
Yes, can I have a question?
Yes, please.
Thank you very much for the very interesting presentation. Actually, I'm doing the really relative the research and development activity.
Thank you.
And I have a question about the number of nails. Do you think if you could increase the number of nails, the climbing performance would also be improved? How do you think about this?
Yes, and thank you for the question. You mean the nails of numbers?
Yes, right now, our current design looks like has 3 nails per
Okay.
gripper, right?
And the foot grasps the objects of the robot weight only. So we wanted to reduce the friction as small as possible. That's why we use 3 nails and 3 as magnets. And nails is increased, and the robot legs and resistance is also increased. In this robot, 6 nails cannot be pushed the sliders, I think.
Okay, so there is another mechanical constraint to design this mechanism. I understood.
Another design. Yes,
if you increase the number of nails, the robot should perform more strong pushing force to grasp, right?
Yes.
Okay, understood. Thanks.
Thank you for that. Next one.
Okay, so other question? Any other question or comments? Okay, so please, Kono.
Thank you for your presentation. Why is the proposed robot?
Thank you.
Why is the proposed robot more effective on the slope than on the flat? Your
Flat?
robot experiments slides.
And sorry, could you say it again?
Why is the proposed robot more effective on the slope than on the flat?
Yes. And one idea, I improved the nails mechanism, and now the nails design is sorry, wait. The nails yes, すいません。And nails design is more round. In this,
Excuse me, Mr. Chairperson, and
Yes,
I'm going
please.
to cut into. My name is Mikami, and I'm a supervisor, his supervisor, and I'd like to add some an explanation about that question. So as the experiment showed, it is okay to move to achieve a better performance both in the slope and the flat area. But because this mechanism bites on the ground, so we think it should be better to use the slope than the flat area. Of course, it would be good for flat area, but in case of a very steep slope, it should be used to grasp or catch the ground by the mechanism, so that we think that mechanism would be good for slope. And also good point is that it would be used both in the flat area and the slope without controlling, without interfering into the robot controller, because it's merely shoots on the robot. Is it okay to your question?
Thank you for very much.
Thank you.
Thank you.
Okay, so as time has passed. Okay, and thank you for great discussion. Okay, thank you.
thank you.